Okay. Good morning, everybody. I am Renee Yager. I'm the Director of Marketing at EPC. And welcome to today's webinar, GaN, Driving Changes in Automotive Systems. Before we get started, I'm just going to go over a few housekeeping items for today's event. Everyone will have the opportunity to submit text questions to our panel by typing your questions into the Q&A feature that you can find at the bottom of your screen. You can send your questions in at any time during the presentation. We'll collect these and address them during the Q&A session at the end of today's presentation. At the conclusion of the webinar, we will be selecting one participant at random to receive a copy of the 3rd edition textbook, GaN Transistors for Efficient Power Conversion. If you're the lucky winner, we will contact you in the next few days for your shipping information. Now, I would like to introduce our panel for today. We have Marco Palma, Director of Motor Drive Systems and Applications, located in Turin, Italy, and responsible for field application engineering in Europe. Marco has over 20 years of field experience within the semiconductor industry, working with customers to define innovative solutions to meet the unique challenges of each customer design. Most recently at EPC, in addition to customer support, he has been involved with application support using the eGaN power stage in motor drive designs. Welcome, Marco.
Hi, everybody.
And our speaker today is Alex Lido. Alex is the CEO and co-founder of Efficient Power Conversion. As a co-inventor of the HEXFET power MOSFET, Alex holds many patents in power semiconductor technology and has authored numerous publications on related subjects, including co-authoring the first textbook on GaN transistors for efficient power conversion. Alex, thank you for joining us today.
Thank you, Renee. All right, and welcome to everybody. In this webinar, we're going to discuss various application areas where GaN technology and devices are improving automotive systems. So first, we'll discuss how GaN-based 48-volt to 12-volt 3-kilowatt converters reduce the size, increase the efficiency, and lowers the cost for 48-volt mild hybrid systems. Next, we'll show you how GaN-based 2 megahertz converters reduce power losses by 40 to 50% for automotive infotainment systems. We'll show you the advantages that GaN can bring to brushless DC motors for the myriad of motors that are inside a vehicle today. And for the last application, we'll show eGaN devices and how they enable Lidar and other automotive time-of-flight systems by providing higher resolution, greater distance capability, and low cost. From there, we'll discuss 3 critical topics for automotive applications: thermal management, EMI, and reliability, including AEC qualification. GaN devices are AEC Q101 qualified and offer improved performance over the aging silicon MOSFET that's used in vehicles today. And that enables higher efficiency, higher reliability, with power densities higher than were ever achievable before. We will look at 4 applications where GaN technology is driving changes in automotive systems: 48-volt for mild hybrid cars, DC to DC conversion for infotainment systems, brushless DC automotive motors, and light detection and ranging used for autonomous navigation. First, mild hybrid cars. By 2025, 1 of every 10 vehicles sold worldwide is projected to be 48-volt mild hybrid. 48-volt systems boost fuel efficiency, deliver 4 times the power without increasing the engine size, and reduce carbon dioxide emissions without increasing system costs. These systems will require a 48-volt to 12-volt bi-directional converter with power ranging from 1 kilowatt to 3.5 kilowatts. And the design priorities for these systems are size, cost, and high reliability. For 48-volt bus systems, GaN technology increases the efficiency, shrinks the size, and reduces system cost. Due to the fast switching speed, GaN-based solutions can operate at 250 kilohertz per phase, as opposed to 125 kilohertz per phase for traditional MOSFET solutions. Higher frequency allows a smaller inductor value. And in this example, it's 2.2 microhenries versus 4.7 microhenries in the MOSFET version, and the smaller inductor DC resistance is 0.7 milliohms versus 1.7 milliohms for the MOSFET version. And that results in less losses and smaller size for the GaN-based solution. The added efficiency from the GaN devices also enables a reduction in the number of required phases. As an example here, in a 3 kilowatt 48 volt to 12 volt DC to DC converter, the higher frequency and higher efficiency results in the reduction from a 5-phase MOSFET system to a 4-phase GaN system, reducing both size and cost. And as seen here, the GaN-based solution is 35% smaller. But with one less phase and double the switching frequency, the EPC eGaN FET solution is also more efficient than the 5-phase MOSFET solution. This graph shows efficiency on the vertical axis versus load power on the horizontal axis. And the eGaN FET solution is 0.7% more efficient at full load. And that's 15% less power loss compared to the MOSFET solution, and 5% more efficient at 10% load. And that's 30% less power loss. And that's a reduction of 21 watts of power loss at full load. The system cost is also reduced due to the ability of GaN to do the same job with only 4 phases versus the 5 phases required for the MOSFET solution. The GaN-based solution is 35% smaller and 20% less expensive than its similar MOSFET-based system. Now, what are the performance advantages that GaN enables in this type of a system level? Well, here we compare 80 volt AEC FETs, the EPC eGaN FET versus the silicon FET in a 5x6 QFN. In this example, the eGaN FETs have 30% lower on resistance and 4 times lower QG or gate charge, 5 times lower QGD or gate drain charge, 0 QRR, and are less than half the size and yet 10 times more thermally efficient. And this means that they can get heat from the device to the heatsink more efficiently. So eGaN technology offers improved performance, amazing reliability, and lower cost compared to the aging silicon power MOSFETs used in today's vehicles. Next, we explore the application of DC to DC converters for infotainment systems. Now, worldwide, shipments of in-vehicle infotainment systems are expected to exceed 183 million units by the year 2022. Modern infotainment systems today contain many advanced features such as touchscreen, Bluetooth communications, digital and high-definition TV, satellite radio, GPS navigation, advanced driver assistance systems, powerful 16-speaker Class D audio, and even gaming. These power-hungry systems put additional demands on the vehicle's overall power system. At the same time, there's limited space inside the dashboard for additional power systems, and there's little tolerance for additional heat generation, despite significantly higher required power levels. GaN devices are very suitable for all automotive DC to DC converters used in this application, with input voltages from 12 volts to 24 volts, because of the point of load needs to switch at 2 megahertz to avoid interference with the AM band. In hard switching applications, like the buck converter, the very low gate to drain charge, or QGD, and switching losses of the eGaN FETs result in considerable improvements in efficiency and thermal efficiency. And let's see how much. One approach to meeting the size constraints of these systems is to go to higher frequencies. GaN devices are very suitable for infotainment DC to DC converters because they can efficiently be switched at 2 megahertz. And that's the frequency required to avoid interference with the AM band. In hard switching applications, such as the case with low cost and high power density buck converter topologies, the very low gate drain charge, or QGD, and low switching losses of eGaN FETs results in considerable improvement in efficiency. Heat generation is also improved compared to MOSFET solutions. In this slide, you can see an example of the efficiency improvement achievable with eGaN devices versus the silicon MOSFET for 12 volt to 3.3 volt and 10 amperes, as seen in a typical infotainment application. Efficiency here is plotted on the left side vertical axis with each graph, power loss on the right side vertical axis of each graph, and output current is on the horizontal axis. At 12 volts to 3.3 volts using eGaN FETs instead of silicon MOSFETs, there's an almost 5% efficiency improvement and a savings of 2 watts, or 50% lower power losses. Additionally, the eGaN FET solution runs 10 degrees C cooler. There are on average 10 electric motors per car for operations such as door locks, trunk latches, retracting roof, gas pumps, ventilation, battery management, heating control, electric steering, and that's just to name a few. Brushless DC motors are simpler to maintain, more durable, smaller, much more energy efficient, and are able to respond faster and at higher operating speeds, and they're considerably lighter in weight. Brushless DC motors are also less prone to the types of failures experienced by brushed motors, thus leading to lower warranty costs. As cars migrate to a 48-volt bus architecture, brushless DC motors become even more attractive for power levels between 30 watts and 1 kilowatt compared with brushed or AC induction motors. The value for eGaN devices in powering 48-volt automotive motors is that they can reduce the size and weight of the motors, work efficiently at frequencies above the audible spectrum, have better torque, and higher efficiency, leading to better fuel efficiency. In March 2020, EPC introduced the EPC 2152 e-power stage, and it's a monolithically integrated 80-volt input half bridge, which includes drivers, level shift, synchronous bootstrap circuit, input logic, all ideally suited for brushless DC motors below about 500 watts. By integrating several functions onto a single chip, the entire brushless DC drive can be made with just 3 power stage ICs, a digital controller, plus sensing and filtering elements. Now let's see some video footage of this demo in action, which shows how much quieter the GaN-based motor can operate due to the ability to significantly reduce just the dead time in the circuit.
Here I want to show you a simple demo of motion control with the gallium nitride devices and gallium nitride IC EPC2152. This board here is the inverter, three-phase inverter based on EPC2152. The same board is there, and here you can see an adapter board for a microchip DSP and a programmer for the DSP controller from microchip. And here I have a servo motor connected to the EPC2152 demo board. So with gallium nitride and with a 50 nanosecond dead time, which is achievable only with gallium nitride, it's possible to get really silent operation. Now I changed the dead time of the modulation to be 50 nanosecond, which is achievable only with the gallium nitride devices, and I will show you the difference in terms of acoustical noise versus the 1 microsecond. So with gallium nitride and with a 50 nanosecond dead time, which is achievable only with gallium nitride, it's possible to get really silent operation.
Thank you, Marco. Now let's move on. Lidar has been used for decades in military, aerospace, robotics, and meteorological fields. In recent years, it's quickly become a key technology to enable autonomous driving. A contributing factor to this has been the advent of commercially available GaN FETs and integrated circuits that enable the laser to be driven with high current pulses with extremely short pulse widths. The short pulse width leads to higher resolution, and the higher pulse current allows the LiDAR system to see farther. These two characteristics, along with their extremely small size, make eGaN FETs ideal for LiDAR. There are a few key GaN FET parameters that drive the feature benefits of the LiDAR sensor beyond what silicon can do and make LiDAR superior to radar for advanced driver assistance systems. First, GaN can handle very high peak currents, which increases the distance capability. Next, GaN has very low gate charge, extremely low gate resistance, and incredibly low inductances. All of these feed into the image resolution and frame speed of the LiDAR system. Lastly, GaN devices are provided in chip-scale packaging to allow designers to place the GaN driver circuit very close to the laser, allowing for very quick transitions which improve frame speed and resolution. The very perceptible difference between a GaN-based system and a silicon-based system can be seen here in these images. Now, this figure represents the state-of-the-art for long-distance direct time-of-flight, or DTOF LiDAR. Here we show a 135 ampere laser current pulse with a pulse width of only 2.5 nanoseconds. This high current capability and short pulse width in combination enables 300-meter visibility with centimeter resolution. For close-up, high-precision LiDAR applications, indirect time-of-flight, or iTOF LiDAR, can be attractive. Often referred to as flash LiDAR, it can capture an entire megapixel frame at one time. These LiDAR systems do not need the extreme power of long-range DTOF LiDARs, but they benefit from the extremely fast edges and very high pulse repetition frequencies. As an example of a short-range LiDAR pulse generated by eGaN FETs is shown here. The blue oscillogram trace is the drain source voltage across the FET as it turns on and off. Note that the 10 ampere pulse has a rise time that's only 556 picoseconds, and the fall time is only 203 picoseconds. For iTOF LiDAR systems, pulse repetition rates can be as high as 100 megahertz, and therefore nanosecond pulse widths are essential. Now that we've shown the many automotive applications where GaN can bring benefits, we're going to talk a little bit about the three key questions for automotive market: thermal management, EMI, and reliability. First, thermal management. Even though our devices are very small, thermal is not a concern due to the excellent thermal properties of our eGaN die. On the left, you can see that the thermal resistance to the printed circuit board, or PCB, is similar to FETs. However, on the right, we are comparing thermal resistance to case against the absolute best thermal package available for MOSFETs, the direct FET. The eGaN devices are 6 times better than the best in-class direct FET because eGaN die can dissipate heat through the PCB, through the top, and out the lateral sides. The lower thermal resistance results in incredible thermal performance. Here you can see that a tiny 4 millimeter square die can dissipate 6 watts with temperature rise of only 24 degrees Celsius, or 4 degrees C per watt. A lot of additional information on thermal handling can be found on the EPC website, including a complete seminar on thermal designs. For motor drives, size and cost dominate, and efficiency is dominated by the motor. Therefore, a key objective for many applications is to drive the most current in as small a volume as possible. And this excellent thermal performance makes that better than any other solution. Now, this next topic is a question we get all the time due to the super fast switching speeds of eGaN devices. What about EMI? And we'll discuss the effect of specific design choices on EMI generation and propagation, such as source size, layout, rise and fall times, and reverse recovery. First, let's look at the effect of source size. And by that, I mean the size of the area of the power loop. EMI must get from the switching transistor to the PC board conductors, leading to the outside world, and must radiate to a transistor from the transistor source. The coupling to the outside world increases with the size of this source radiator. Reducing the size of the power loop reduces this EMI. The power loop is always bigger if the FET is used, the MOSFET is used, because the MOSFETs are much bigger than the GaN devices. So the loop for the GaN-based solution on the left, as you can see, is significantly smaller than the MOSFET version on the right, and that leads to less radiated EMI. Now here we look at a zero-cost adder for EMI avoidance. When designing converters, the layout will inherently have parasitic inductance. In this example, with a synchronous buck converter, we show the effect of loop inductance, power loop inductance on the voltage overshoot of the switch node following a rising edge hard switching transition. Now in the left image, with a loop inductance of just 1 nanohenry, this results in a 70% peak voltage overshoot with ringing. Now to put this in perspective, a PQFN package will have 1 nanohenry of inductance inside the package. So you can't get better than that with a MOSFET solution. So here we have, in this case, 1 nanohenry of total loop inductance, and you get a 60% peak overshoot with ringing. Now on the right image, we have a loop inductance of 400 picohenries, which you can achieve easily with eGaN FETs. And that results in a 30% peak voltage overshoot with some ringing. Now the EMI generated is proportional to the square of the magnitude of the rising edge voltage. And it typically propagates as an E field emanating from the conductors that form the capacitors with the ground potential. The loop inductance will also conduct a current during the ringing period with corresponding EMI generated that's proportional to that current magnitude, and it typically propagates as a magnetic field or H field emanating from the power loop circuit. So reducing the power loop inductance by half will reduce the EMI generated by more than a factor of 2. Now for a third element, let's look at switching transitions. eGaN FETs switch much faster than MOSFETs, and many ask the question about how this affects EMI. It's important to note that there's fundamentally no change in EMI energy simply because one device switches faster than another. There's only a shift in the spectral content. And this can be shown by an example using a buck converter again, operating at 1 megahertz, converting a 48 volt input voltage to 12 volts for 2 switching transient conditions. In this case, 5 nanoseconds and 1 nanosecond respectively. The graph shows the spectrum of the switch node voltage for both transient conditions, and with the rising edge time set as exactly the same as the falling edge time. And it excludes all voltage overshoot and ringing. So we're just looking at the switching transitions and its contribution to EMI. And it can be seen on the graph that at 90 megahertz, the spectral content has already attenuated by 42 decibels. In the 5 nanosecond transition case, the first frequency node is at 200 megahertz or 1/5 nanoseconds. And in the 1 nanosecond transient case, the first frequency node is 1 gigahertz or 1/1 nanosecond. And the rate of decrease in spectral magnitude above these frequencies is 40 dB per decade, which means that filtering requirements are already very low to begin with, and it makes it very important to address this voltage overshoot ringing discussed earlier. That is a much bigger factor than these rising and falling edges. The switch node effectively forms the plate of a capacitor with the ground being the second plate. So this form of EMI E-field is radiant dominated. Now, here we talk about the often overlooked impact of reverse recovery on EMI using a hard switch buck converter as an example. Reverse recovery it manifests itself as a shoot-through current in the power loop. And as was shown earlier, the current in the power loop leads to voltage overshoot and ringing. The reverse recovery adds to the energy in the power loop and thus adds energy to the EMI noise source, and is proportional to the square of the reverse recovery current, to the square of that current. Now, this reverse recovery current can be several times higher in magnitude than the inductor current of the buck converter. The left waveform shows the voltage overshoot and ringing for a MOSFET. Okay, and this is in a buck converter with a dead time of 5 nanoseconds, 20 nanoseconds, and 40 nanoseconds, which is far more typical for a MOSFET-based buck converter. And the eGaN effect equivalent is on the right waveform under the same operating conditions. And it can be seen on the right waveform that a change in dead time has no effect on the eGaN FET because it has zero reverse recovery. So in summary, eGaN FETs and ICs are very EMI friendly. eGaN devices are 5 to 10 times smaller than their aging MOSFET ancestors, and this size advantage translates directly to the smaller layout area that radiates less. By adopting simple layout techniques, you can ensure that there is significant reduction in EMI generation, and it adds zero cost to the design. The higher switching slew rates only result in a shift in spectral content, but do not increase EMI energy. At higher frequencies, EMI reduction techniques are more effective, ensuring lower cost to implement. And finally, eGaN FETs and ICs have zero reverse recovery, and this inherently generates less EMI energy in hard switching converters. So let's move on to the final topic, which is reliability. And it's a critical question for any application, but particularly important in automotive applications. So we'll show that GaN is actually more robust than silicon. We'll start with a quick overview of the test-to-fail methodology that EPC employs, and next we'll discuss the impact of voltage stressors on reliability. We'll evaluate safe operating area tests used to verify that devices can be operated without failure at every point within the datasheet SOA graph, and then we'll look at the impact of current stressors on reliability. And lastly, we'll show you the most important reliability measure, and that's what customers see in the field. Standard qualification testing, including AEC Q101 testing, typically involves stressing devices at or near the limits specified in their data sheets for prolonged periods of time or for a certain number of cycles. The goal of qualification testing is to have zero failures out of a relatively large group of parts tested. This type of testing is inadequate since it only represents parts that passed a very specific test condition. So by testing parts to the point of failure and understanding the amount of margin between the datasheet limits that's developed, and more importantly, and understanding the intrinsic failure mechanisms, we can find the root cause of failure and therefore characterize the device behavior over time, temperature, electrical or mechanical stress. We can understand the safe operating life of a product over a more general set of operating conditions. So let's look at a couple of examples. Using our test to fail methodology, we took devices well beyond their datasheet limits and monitored how they failed. For gate voltages, we took groups of devices and biased them at 8 volts, 8.5 volts, 9 volts, and 9.5 volts, well beyond the datasheet limit of 6 volts, and measured exactly when those devices exceeded the datasheet limits for the gate. With that data, we can generate these graphs. On the left-hand side, we show the mean time to failure for devices versus gate voltage at 2 different temperatures. And on the right-hand side, we answer the question, what's the time to failure for a certain percentage of the gate device, certain percentage of the devices versus gate bias? In this case, we took the automotive qualified EPC 2212 as the representative device, but all of our gate structures and all of our devices are essentially the same. And we verify that they behave essentially the same way as well. An important thing to note is on the left, we see very little difference in the failure rates at 25C or 120C. In other words, the gates are not very sensitive to temperature. And we also notice that as you go to higher gate bias, the failure rate, of course, increases, and the mean time to failure goes down. On the right-hand side, we show that same thing in terms of percentage of failure. And we drew a vertical red line to show the maximum rating of our devices, 6 volts. And you can see that the first diagonal green line that says 1 ppm, and that's our prediction when you'll see 1 part per million of failure in our device, in the failure of our gates of our devices. Now, if you follow that 6 volt line up to the dotted line that says 10 years, you'll see that at 10 years, we expect 1 part per million failure at approximately 5.25 volts on the gate. So if you put 5.25 volts DC on our gate and you waited 10 years, you'd see 1 part per million failure or less. Now, this is a very stringent kind of a test. And the fact that we rate our devices at 6 volts, where at 10 years you'd see about 20 ppm failure, is a much, much more stringent way to spec a device than the way power MOSFETs are rated. And it's one of the reasons why to this date, 10 years after we started production, we've seen 0 field gate failures, 0. Now let's look at drain to source stress. And once again, using this test to fail methodology, we took a bunch of devices and biased the drain to source at the rated voltage or beyond. And in this case, it's with the EPC 2016C. And we took them to 100 volts and then well beyond the datasheet limit, all the way up to 130 volts. By extrapolating to when these devices will cross the datasheet limit, we can create a time to fail. Now, when you're at 130 volts, the devices exceed the datasheet limits pretty quickly, and the key failure mechanism is on resistance. So you can measure the actual time it crosses the datasheet. And these data points can be translated to the graphs into these graphs. And on the left-hand side, you have the time to failure for various percentage failure rates. So 0.0001%. Now that's 1 part per million. And 1%, you know what that is. And so we drew a 20-year horizontal line on this one. And as you can see at the 100 volt rating of the EPC 2016C, we would expect that devices would see less than 1 part per million failures in far more than 20 years, hundreds of years actually. However, if you look at the error bars, you'll see that the error bar dips under the 20-year line to a little bit less than 10 years. And that's the 90% probability line. So with 90% probability, we can say you'll see better than 1 part per million failures at the rated 100 volts under DC bias in about 10 years with these devices. Now, for many years, it's well known that MOSFETs, those aging silicon MOSFETs, have a second breakdown characteristic. With MOSFETs, as you go higher and higher voltages, the safe operating area, as defined as the current on the vertical axis, the drain source on the horizontal axis, has a bend in it. Okay. Now we've drawn 45-degree lines on these graphs, and those are lines of constant power. But MOSFETs can't take constant power at higher voltages. And that's because of a secondary breakdown characteristic caused by the rapid decrease in threshold voltage of these aging MOSFETs. And this threshold voltage goes down with temperature. Now at EPC, we developed testing and where we failed devices. And you can see the green dots are 100 microsecond pulses that pass these tests. In other words, devices survive, and the red circles are where those devices fail. And they all fail above the constant power line. The triangles are for the 1 millisecond pulses, and you can see that they all fail above the constant power line as well. We've done this same test for a whole variety of devices, and the results can be found in our Phase 11 reliability report on the EPC website. But be assured that every point in the SOA curves on our data sheets can be utilized by our eGaN FETs. Now, short circuit robustness refers to the ability of a transistor to withstand unintentional fault conditions that may occur in a power converter while in the conducting state. In a short circuit event, the part can experience the full bus voltage combined with a current that's limited only by the inherent saturation current of the transistor and the circuit parasitic resistance. If the short circuit state is not quenched by protection circuitry, the extreme power dissipation will ultimately lead to thermal failure of the FET. The goal of short circuit testing is to quantify the withstand time, how long the part can stand without, or how long the part can survive under these short circuit conditions. And here we've taken two devices, the EPC 2051 and the AEC Q101 rated EPC 2203. And we applied a short circuit with either 5 volts on their gates or the maximum 6 volts on their gates. In the worst case, with 6 volts on the gate, the EPC 2051 lasted 9 microseconds before failing, which is plenty of time for a protection circuit to turn the device off. On the vertical axis, you can see that under all of these short circuit conditions, the devices only failed when junction temperatures exceeded 800 degrees C, and the device was dissipating over 4 kilowatts of power. Now, these are tiny 1 millimeter square devices, 1 millimeter square devices. So that's another illustration of just how robust eGaN transistors are under just extreme conditions. As of the Phase 11 report, we had 123 billion device hours documented in the field under use since January 2017 in just automotive and telecommunication applications. And we have a total of only 3 device units that failed. These 3 device units failed for an extrinsic failure mechanism. In this case, it was a minuscule defect in the wafer fab that has since been fixed. No MOSFET has ever come close to this level of reliability, ever. Now, EPC has a growing portfolio of eGaN FETs that are AEC Q101 qualified for use in automotive applications. These initial products will be followed by a constant stream of transistors and integrated circuits that are designed to enable autonomous driving and improve fuel economy and safety. eGaN technology is faster, smaller, more efficient, and more reliable than the aging silicon power MOSFET used today in vehicles. In summary, eGaN technology is driving significant changes in a variety of automotive systems. GaN makes smaller, more efficient, and lower cost 48 to 12 volt bi-directional converters required in mild hybrid cars. GaN reduces power losses by 40 to 50%, providing more efficient operation at 2 megahertz, which is above the AM band, and that's for converters used in infotainment and ADAS systems. The value of GaN devices in powering 48 volt automotive motors is reduced size, weight, and efficient operation at frequencies above the audible spectrum. GaN technology is the solution, creating high resolution, long distance LiDAR systems for next generation vehicles employed in advanced driver assistance systems and autonomous navigation. In this webinar, we showed a simple, inexpensive thermal system to maximize the power you can get out of these tiny eGaN devices. And eGaN is also very quiet when it comes to generating unwanted EMI. And lastly, and very importantly, we showed that GaN demonstrates field reliability that is unmatched by silicon power devices used today in automotive. And for more detailed information about GaN FETs and ICs in automotive applications, please go to our website, epc-co.com.
Okay, thank you, Alex. So now we're going to begin answering the questions that were submitted during today's presentation. As a reminder, you can still submit questions by typing them into the Q&A feature at the bottom of the screen. So Alex, our first question is, what are the barriers to develop a 1200 volt GaN device?
So there actually are. I think Visic in Israel has a 1200 volt GaN device. I'm not sure if it's in production, but they've advertised it. So there are no barriers. The question is whether or not that's of great value to the world. And my opinion is that when you get to above 650 volts, GaN devices, which are lateral in order to be very efficient, become less efficient than, for example, silicon carbide transistors. So I think that above 900 volts, certainly, silicon carbide is your best choice. And below 650 volts, gallium nitride is your best choice. And between 650 and 900 volts, it might be GaN, it might be silicon carbide, it might be silicon CoolMOS, and it might be silicon IGBTs.
Okay, we have a two-part question. What's the typical DVDT at switching point, and how do you control DVDT without using filters?
So, first of all, I'm going to answer the first part. There's no typical DVDT. And we have actually in production, customers have circuits that have DVDTs as high as 300 volts per nanosecond. So quite extraordinary DVDTs. However, those aren't always necessary and they're not always desirable. So I'm going to ask Marco to answer the question, how do you control DVDT, for example, in a motor drive?
Yeah, in the motor drive, it's basically changing the strength of the gate resistor if it is a discrete approach, or in the integrated circuit, we also have a capability to have the resistor that is shaping the DVDT. And just for your information, in the case of a motor drive, the demo board that Alex showed just before with the EPC 2152, I'm getting 10 volt per nanosecond, which is quite common in typical motor drive applications. It's not that something exotic, okay? So there are basically two philosophies. One is going as much as fast as the GaN can do, and then using an output filter. That's one philosophy. Then the other philosophy is just slowing it down to, as I said, 10 volt per nanosecond or in that area, and not using any filter at all. And what really matters is having a very good low inductance in the power loop, so to reduce the ringing and having a very nice switching waveform.
Okay, the next question is, the input filter for CE will be of smaller size and cost, but the energy at higher frequencies will just couple through the filter with that fast switching. Do you have EMI reports with CISPR 25 settings?
Marco, do you know the answer to that one?
Yeah, in that case, so in this moment, really the EMI reports really depends on the specific circuit, okay? We don't have it. There are one general thing, by the way. Yes, there's one difference if you compare to MOSFET. In the layout, when you working with GaN FET, need to be very well done by following our rules, because it's different, new device that needs to be driven in the right way. And also we have high frequency capacitors very, very near the device, because the device is chip scale package. It's in really making the inductance small. And so that it's not really said that at the end of the day, the input filter is suffering because of this high frequency. This really needs to be proven in a real lab with a real circuit and making some comparison.
Okay, thank you. Is the input decoupling comparable to MOSFET requirements to pass EMI, or does GaN require more attention to the capacitors to absorb the high frequency currents?
I think that first of all, the high frequency currents in GaN devices are smaller than they are in MOSFET, so you can use much smaller capacitors. In many cases, you can go to ceramic capacitors and other high frequency components that are not only small but very reliable. So the basic thing is GaN emits less EMI. And you can take advantage of that by going to higher frequencies, which makes everything smaller and easier to filter out in general. So you're in good shape with GaN, and then you can also be in good shape even at very high frequencies. Marco, you want to add anything to that?
No, just one minor thing, that's something that cannot be done with conventional technologies. With the chip scale packages, the circuit is so small that then you can place high frequency capacitor and do the optimal loop layout that Alex shown. And that is really a key difference, because then really there's no overshoot, there's no ringing, and the switching voltage is very good. The waveform is very good. Then it's reducing the EMI.
Yeah, we said it in the seminar just a minute ago, but I just want to reemphasize: chip scale packages have no internal inductance. When you have a MOSFET, the internal inductance alone is more than the entire power loop inductance in a GaN circuit. So you're going to get ringing and overshoot, and you're probably used to that if you use MOSFETs. So you think, well, that's the fundamental. Well, it's not. It just becomes very quiet if you use our layout guidelines. It becomes very quiet. And then you don't have that added effect of this body diode that just pumps a lot of current into your circuit, causing more EMI ringing. So it just quiets everything down, and then you can go up to much higher frequencies and use smaller components that are more reliable.
Okay, so speaking of high frequency, that kind of leads into the next question very nicely. What about the high frequency magnetic material availability in the megahertz range?
So, you can, on our website, we have lots of information on that. We have some 10 megahertz buck converters, and we have good discourse on magnetic materials. What we've seen in the last 10 years is tremendous improvement in magnetic materials. I think it was primarily driven by the desire to go to higher frequencies in power conversion. So, it used to be that the common thought megahertz, you have reduced returns from going to higher frequencies because of magnetics. And now I would say that number is maybe 2 to 4 megahertz. You can get increased efficiency without a big drop off in magnetics in DC to DC converters. Marco, what do you think?
Yeah, I agree. And really, the offering from all the vendors increased a lot in the last 5 years. Clearly, there's a market trend going there. If you're looking historically, the CDC converter were occupying a lot of space in the past because of big bulk capacitors and big bulk inductors. And then the capacitor technology changed, it became better and smaller. And then now it's time to the magnetic component to get into that same shape together with the gallium nitride devices. So that's clearly happening. It's a clearly consolidated trend, and it's becoming more and more offered for all the magnetic components producers.
And the world record right now we have in mass production is hard switching amplifier that's running at 75 megahertz hard switching using an air core inductor. So there you can go way up there. We have many applications in the 1 to 3 megahertz range using magnetics. I think that problem's been overcome maybe in the last 5 or 6 years.
Okay. Next question is GaN devices, are GaN devices capable of working satisfactorily in the linear mode?
The answer is yes. We have a few applications in the linear mode. I think that you're just not taking very much advantage of the GaN that we designed, which was meant to be a switching transistor. But because they're so thermally efficient, we have some people that use them, yes, in the linear mode. And feel free to do that. Because of that wide SOA, that safe operating area that we showed, they're far superior to a MOSFET in the linear mode. That's for sure.
I may add one thing. The SOA of the GaN FET, it's really square SOA. There's no second breakdown effect. So that's easier than doing with MOSFET. And there may be some application like for instance, some cases where the device needs to be full on all the time because it's the application requiring it. That's something that can be easily done.
Now, one thing I'll add is that the FT of our devices, the largest devices have FTs of about 2 gigahertz, and the smallest ones are up 6+ gigahertz. We even have a family of 8000 series where the FTs are around 10 gigahertz. So, as you use them in the linear mode, you have to be careful that these things are very, very fast.
Okay. Next question is, do you have any plans to automotive qualify the power stage device that you showed?
Yes, we do. We want to automotive qualify everything that our friends in the automotive industry want to use.
Okay. What about anti-parallel external silicon diodes used in motor BLDCs and Class D applications? Should those be added to eGaNs or not?
Marco,
may I take this?
You could answer that one. Yeah.
Yeah. So the anti-parallel diode, it really depends on where the motor has to be used. Okay, because if in the application, the final application, there are conditions where the inverter itself is not powered at all. So there's no DC bus and the motor can be used as a generator. I'll give you an example. If it is a fan which is placed outdoor, and then you have what is called the typhoon effect, then the fan starts rotating because of the big strong wind outside, and that's creating energy which is being rectified by the inverter. So from that point of view, then it would be a little bit more conservative adding anti-parallel diodes. If there's no such a kind of a case in the application and the bus is always present or it's just going away when the system is switched off, that there's no need to put it.
Okay. Next question is, are there PFET replacements available?
I'm assuming that means P-channel FETs, and the answer is no. Gallium nitride is very, very efficient at conducting electrons, and that's an N-FET or negative carrier FET, and extremely inefficient at conducting with holes, which are positive charges, which lead to P-FETs. There are ways around it in very low power applications. So it's conceivable that you'll see in the next few years CMOS using GaN, which uses both PFETs and N-FETs. But I don't anticipate you'll ever see power devices, P-channel power devices in GaN.
Do you have any plan to add SOT23, SC70, SOT26 dual packaging to your portfolio?
No, we don't. As a matter of fact, if you look at our portfolio, it's all chip scale packages. And we are AEC Q101 qualified with our chip scale packages, and there's a good reason. Our chip scale packages are actually glass sealed devices. Because GaN is built on top of silicon, you can actually seal them in glass on top of the silicon wafer before you cut them out of the wafer. And therefore, they are very inert to any kind of environmental condition. All our devices are MSL1, which basically means you can throw them down to the bottom of the ocean for a century and they'll still work. They pass, humidity testing. They pass every test that any package will pass. So, what do you want the package for? Because packages add size, they add cost, they add resistance, they add inductance, they add thermal resistance, and they are a reliability hazard. So you got 6 good reasons to not want to have a package. And I encourage you, therefore, to use our chip scale packages and get rid of all that nonsense of your SOT 23s.
Does EPC have any plans for 600 volt GaN?
Not at this time. We're really looking at the medium voltage under 400 volt range. It doesn't mean that there isn't good market above 600 volts, but there are lots of people doing that. So, we wanted to specialize more in the area where people are more sensitive to, wanting to go to higher frequencies, smaller size, where we see GaN having great strength.
We have time for one more, and it is, what do you have recommendations for automotive qualified drivers for your eGaN FETs?
Yes, I believe TI has automotive qualified, the 5113?
The 5113Q, and they also have the LMG 1025 Q1, which is I think that's their high speed one for.
Yeah, that's a high speed low side or single side driver. The 5113 Q is a half bridge driver, and both are excellent products.
Okay, well, we're going to wrap up. Thank you, Alex. Thank you, Marco. Thank you, everyone, for attending and also for your great questions. Likewise, if you have any additional questions, please send them into info@epc-co.com and we'll get them over to the panel to answer. Once you leave today's webinar, you will receive a survey on the presentation, and we would appreciate if you could spend a few minutes and give us your feedback. You'll also receive a follow-up email within 24 to 48 hours with a link to view a recording of today's webinar. There's also another series of webinars that will be continuing through the rest of the end of the year and going into Q1 of 2021. So be sure to check back at the EPC website for that calendar of events. It's www.epc-co.com. Again, thank you for joining us today. We hope to see you again at the next webinar. Visit us at the website for more information and have a great rest of your day. Thanks, everybody. Thanks, Alex. Thanks, Marco.
Bye-bye.
Bye.